Hi everyone. So welcome to supplementary videos 19. And in this supplementary video, what we will do is we will try to reconcile the scaling relationships that you have been seeing in your different problems you have done in homework, in class, and recently for unconfined flows in the last week in the lectures. And you will also solve similar problems in your homework, last homework 6. Okay. My basic aim for this video is to kind of show you that there are great similarities between confined flows and unconfined flows, and how you should kind of think about that, in a very kind of unified way rather than thinking of these two as separate class of flows. So let's start with the confined flow. So the first problem we did in the confined flow, the non-uniform velocity, was the case where you had a parabolic profile like this, right? We say that the flow is fully developed entirely, and the temperature was something like this, where this is delta T. And what I will do is I will use a bit of, the coordinate system that I had kind of introduced in supplementary video 18, which is that we will use y direction as perpendicular to surface and x direction as parallel to surface to solve these systems. Okay. So now in kind of like, in this coordinate system, this is the x direction and this is the y direction. So the r direction or the radial direction becomes the y direction, and x direction becomes the flow direction. And the idea being that this is what's, our system uh, 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 basically is seeing as sort of a thermal boundary layer within a fully developed flow. And what we want to find is Nusselt's number, and as we have discussed, that Nusselt's number in this case would basically be given by R by delta T. Okay, and this is typically the case that you have the thermal boundary layer one by thermal boundary layer times the dimension of the system. So in this case, it's the radius. In the flat plate cases, it's the length, and so on. And that's Nusselt's number, and that's what we want to find. Okay? So recall that if whenever you want to estimate the velocity, so one thing is delta T by R is much smaller than 1, because Speckley number in this problem was given as to be as much greater than 1. And if this is true, then we know the condition delta T by delta M is much smaller than 1 is satisfied, because the momentum boundary layer in this case is fully developed. So it's basically the system length scale, which is the radius in the system. So this is true. So we can use the Taylor series expansion. So we have Vx at y equal to delta t is Vx at y equal to 0 plus del Vx by del y at y equal to 0, and delta t plus del square Vx by del y square delta square by 2 and plus so on. Okay. And in this case, we know it's a solid surface. So we know that this is actually no slip. So no slip is allowed. So we can say that the Vx in the thermal boundary layer will scale as del Vx by del y times delta t. Okay. And we also know that the delta y in this case would be, or the sorry, the del Vx by del y, or the shear rate rather than for the velocity scale, would be u by r, right? Because in this case, velocity changes at the scale of velocity changes throughout the cylinder, throughout the pipe, right? So that's why this is u by r times delta t, and that's the scale of Vx. Now, whenever we want to do the analysis and get to estimate delta t, we simply use the formula that Vx del t by del x will roughly scale as alpha del square t by del y square. And note that this Mark did this several times in the class, so I'm not repeating myself. There will be a term of Vy plus Vy del t by del y, but that has the same scale as Vx del t by del x. And in the right hand side, we will basically only get the normal direction, because delta t by r is much smaller than 1. So Mark did this in class. I invite you to again check out his lectures and see that. But this is what you always get. And essentially, you will get here u delta t by r. And I'm just calling this length scale of x is x. You can also call it length. That's both are equivalent. And you have delta t times alpha delta t by delta t square. And you get this cancelled out. or essentially you will get delta t cube scales as alpha x r by u, and we want to find delta t by r because our Nusselt's number is r by delta t. So we basically get uh, alpha ur by alpha times x by r. So finally, we get delta t by r as Peclet to the power minus 1 by 3 and x by r to the power 1 by 3. And finally, Nusselt's number thus will scale as Peclet to the power 1 by 3. Just to clarify, Nusselt's number scales by r by delta t, Peclet to the power 1 by 3, and r by x to the power 1 by 3. I've just reversed the x by r. So this is what you get. And you can verify the exact solution looks exactly the same with just a coefficient in front of it. But I really want to emphasize here this point that this is the scale of velocity, and this comes out because of no slip. If we did not have no slip, we will not get out this scale. So this 1/3 scaling, typically when you see this 1/3 scaling delta t cube, why does that happen? That happens because there is a delta t in the velocity and there is always a delta t square from the diffusion. So that's why that makes delta t cube and you get this 1/3 scaling. So 1/3 scaling comes in typically whenever you have a zero velocity on the surface, which gives to this velocity scale, which itself depends on delta t. All right, so they get this speculative times 1 by 3. Now, let's go and see the problem that you did in your homework, which was you had a falling film, you had an impermeable surface, you had c is equal to c naught, so that this was x, so we don't have to change the variables in this case, this was y, this dimension was h, right? And we said that there will be like a delta c here, right? Delta c. So is that delta c by h is much, much smaller than 1 because specular number was much, much greater than 1. And the velocity profile was fully developed. Again, it was parabolic. So velocity profile was like this. Let me use a different color. Maybe let's sketch it a bit down here. Velocity profile was like this. Where you had the velocity like going like this, right? It's zero at the surface and maximum at the interface. Now, note that again we want to find Vx at y equal to delta c. So we'll write as Vx at y equal to delta, y equal to 0, plus del Vx by del y at y equal to 0, delta c, and so on. Now in this case, because our y equal to 0, the place where the transfer is happening, we do not have no slip. So this is not no slip. We have a velocity at the surface, so we will not use this part. This part is only used when the velocity is exactly 0 at the surface, because otherwise there is a contribution coming from the first term, which is very important. And if that term has a scale, so then we can simply say that velocity scale will scale as u, because the velocity, now that's the maximum velocity, right? So that the velocity is maximum here, the velocity will simply scale as u. And now if we do the same problem, which is to estimate delta C, we will say Vx delta C by, so let me just clarify what I'm trying to say. You remember that this is also true here, d del square C A by del y square. So we'll get, in this case, u delta C by x scales as dA delta C by delta C square. This gets cancelled, or our delta C scales as dAx by u delta c square, and in this case Sherwood number would be h by delta c, right? We want to find delta c by h, or dA by uh times x by h. So finally delta c by h becomes factorial to the minus half into x by h half, or Sherwood number becomes factorial to the half h by x to the minus half. This is exactly what you derived in your homework using error function analysis and semantic transform. So again, I want to emphasize here why you get a half scaling. So 1/3 scaling was when you had the velocity being dependent on the thickness of the boundary layer itself. But in this case, velocity does not depend on that because there is no slip. There is just the velocity scale. So we get a 1/2 scaling. And that's the major difference between these two scenarios. Okay. Now let's go further. Now we have been discussing confined flows. What about unconfined flows, right? So let's go to the unconfined flows now. Unconfined flows. In the unconfined flow system, we had a system here which was RE much less than 1 and Peckley much greater than 1. And in that case, we have, we have delta T here where the thermal boundary layer, but the flow was creeping flow. So the flow is kind of like fully developed flow, right? Because the flow is very small, the Reynolds number is very small. So it basically is kind of there, the gradients are only present at the length scale of the radius of the sphere. So the main thing is that we know that the velocity changes at the length scale of the sphere. So now our x would be the theta direction and y would be on the surface. So kind of like this, right? And we'll say again Vy at y equal to delta t is Vy at y equal to 0 plus del Vx by del y at y equal to 0, delta t, and so on. This is no slip because this is a solid surface. Remember, this is a solid surface. In your homework, it is not a solid surface, so you have to use a different scaling. And what we get del Vx by del y is u by, and we said that's the u by the length scale at which the velocity changes. And in this case, it will be the radius of the sphere, delta t. So my mistake, actually, I think I quickly wrote Vy. This is Vx. Sorry about that. Please don't get confused. We're interested in Vx. So the Vx scales as u by r delta t. Okay. And then again, we'll say same thing. Vx del t by del x scales roughly as alpha del square t by del y square. Velocity again, we get u by r delta t by, and delta x in this case will be r because that's the scale of the x direction. Alpha delta t by delta t square. This gets cancelled, and we again get delta t cube. It's proportional to, so it scales as alpha r square by u, and delta t by r whole cube. The scale is alpha by u r. And finally, delta t by r will scale as Becquerel to the power minus 1 by 3, and Nusselt's number is scale as r by delta t will scale as Becquerel to the power 1 by 3. Again, see that because it's a solid surface and we had a thin thermal boundary layer, we got the scale that we have. This velocity scale had a delta t dependence on it because there was no slip in the system, and we again get a 1 by third scaling in the system. And this is really important to kind of differentiate between the two systems, is the fact that whenever we have a fluid solid surface, because of no slip condition where the velocity is exactly 0, we can get this 1/3 scaling out. But in a fluid interface, like the interface you had here, we did not get that scaling. Okay. Now I finally want to discuss two other cases which were again discussed in class in unconfined flows over a flat plate. So I'm now talking about the case when Reynolds number is much greater than 1, Peckley number is much greater than 1, and we have been told that Prandtl number is much greater than 1. So in this case, we were told that delta m will be much greater than delta t. So delta t would be like this because Prandtl number is like this, and we have, this is y, this is x. So we can say here too Vx is Vx at delta t is y equal to delta t is Vx at y equal to 0 plus Vx by del y at y equal to 0, delta t, and so on. Because it's no slip, we can simply ignore this term, and we get Vx here as u by delta m. And this is again where I want to differentiate this case with the other cases, and we get delta t out. Okay. Now we'll use this in our analysis of Vx del t by del x scales as alpha del square t by del y square. Vx is u delta t by delta m, delta t by L. This is the, let's say the length is L here. Okay, and scales as alpha delta t by delta t square. Get cancel this out, and you'll get delta t cube is alpha L by u, and delta t by L is alpha L by u, and also delta m here. You will get delta t by L cube is alpha by ul minus delta m by L. And finally, we get delta t by L is factorial to the power minus 1 by 3 and delta m by L to the power of 1 by 3. Okay. And now let's contrast this case with the case here, what we found here, because it's still a solid surface, it's still an unconfined flow, but the difference here being that our momentum boundary layer thickness in the case of an unconfined flow, in a creeping flow, the momentum boundary layer thickness was just R. There was not dependence on Reynolds number because it's a creeping flow system. So the momentum boundary layer thickness is essentially kind of, it's independent of Reynolds number because it's just constant. It does not change with the length scale or with the velocity scale. But here, now delta m by L scales as Reynolds number to the power of minus half, which then gives you, the final solution, which was derived in terms of Prandtl number and Peclet number. So you can again see a 1/3 scaling, but there's a slightly twist here in the sense that delta m by L is also there because delta m itself is a function of Reynolds number. So if delta m, if let's say in the case of a sphere, this L was this radius of the sphere, and delta m was also the radius. So this ratio here essentially became 1, right? And that's why you basically did not get this an additional factor of a Reynolds number to the minus half in other problems. But you got when Reynolds number is also greater than 1 and Peclet number is greater than 1, is that both momentum boundary layers and thermal boundary layer are changing with the space. Here, only all the previous cases we have discussed, flow was fully developed. Flow was basically not changing. Flow had a constant length scale which was defining the gradient. But now the gradient of the flow itself is changing with the space, and that's why you get this additional Reynolds number to the power minus half, which gives you different scaling. And finally, I want to mention that uh, y and x, if we have Reynolds number greater than 1, Peclet number greater than 1, but Prandtl number much smaller than 1, then we will get the opposite scale of of thermal boundary layer, momentum boundary layer. Thermal boundary layer will be like this, momentum boundary layer will be like this, and the velocity scale would be like this. Now note that I cannot write this expansion anymore. I cannot write this expansion which I have written here because this is not a case where delta t by delta m is much smaller than 1. Because in this case, it's the opposite case. So I'll have to look at the physics of the problem. And in this case, it's very clear that at the length scale of the thermal boundary layer, uh, velocity scale is simply u. And if you do the case of Vx del t by del x, okay, this is L square equal to t by del y square, you get u delta t by L, delta t by delta t square. You simply get this out, and you get delta t by L. In this case, becomes simply alpha by whole square, and this, or delta t by L is better to the power minus half. Okay. So you can verify this. This is just a few mathematical steps. But the point is, in this case, we cannot apply that expansion because we do not satisfy the criteria that thermal boundary layer is small. So I mean, in this case, you can clearly see at the scale of the thermal boundary layer, the velocity is almost always u, except the very thin region, which is not important for scaling analysis. And this gives us again a 1/2 scaling, almost kind of like that there is no slip, right? Because at the scale of the thermal boundary layer, we have a full region, and the solid surface is quite far away. So that's why kind of like 1/2 scaling comes out, which you see basically in systems like fluid interfaces, or where no slip is not valid, or the zero velocity is not valid. Okay. So I hope this video was useful. I was trying to show you like how 1/3 and 1/2 scaling are present in both confined flows and unconfined flows, and you can try to see both of them together. And I also hope this connects back to the how we scale velocity, tangential velocity using the statistical series expansion, whenever the thermal boundary layer, the momentum boundary layer is much smaller than 1. So hope this video was helpful. If you have any questions, please feel free to contact us, and I look forward to seeing you in the next video.